Hi, chemistry students. So we are looking at heating and cooling curves in this video. We have previously seen heat. All right, we kind of had an introduction to that. So heating and cooling curves, you'll see what those look like in just a minute. All right, a little bit of review though. Energy is measured in joules. All right, gets the unit J. So J is for joules. All right, something that we've also seen, the temperature of a substance has to do with its average kinetic energy. The formula for kinetic energy, it's 1/2 mass times velocity squared. All that we have to worry about is when I say kinetic energy, that means the speed of the particles, right? Faster particles, more kinetic energy, higher temperature, all right? Colder particles, lower average kinetic energy, lower speeds, all right? And we've seen this formula. Q equals mc delta T. Q stands for the energy, M is mass, C is specific heat, and delta T is the change in temperature. So if you want to figure out uh, what change would happen when you add a certain amount of energy to a given mass of a substance, you would look at its specific heat and you would determine its change in temperature. All right, so a practice question. How much energy is required to heat 15 grams of water from 10 degrees Celsius to 90 degrees Celsius? The specific heat of water is 4.18 joules per gram degree Celsius. All right, so these are some classic questions we saw in our previous week of study. So we're looking for Q. All right, well, we need M, C, and delta T. M from this question, it's 15 grams. A mass of 15 grams of water. The initial temperature is 10 degrees Celsius. The final temperature is 90, right? So that delta T, that change in temperature, it's 90 minus 10. All right, so the water, it is changing 80 degrees of temperature. All right, so delta T equals 80 degrees. And the specific heat of water is given in this question, 4.18. That's for liquid water. And so Q equals MC delta T. We multiply 15 grams times 80 degrees Celsius times 4.18 joules per grams times degrees Celsius. My grams unit cancels out. My degrees Celsius unit cancels out. I'm left with just joules. 5,016 joules. All right, so pretty straightforward calculation. We've seen these in the past as a nice review to kind of get our minds warmed up. All right, so just some interesting things. You're not going to need the specific heat of multiple different substances, right? So you're not going to need like the specific heat of different metals, which are all very low. We're going to be looking at water. So we want to know, is the water in its solid state, right? Ice. Is it in its liquid state? A lot of times people confuse water for liquid. They say it's water. Well, it's liquid water. That's what we're used to. That's the 4.18. Or is it in the gas state, which we would call water vapor? All right, so solid water has a specific heat of 2.11 joules per grams degrees Celsius. Liquid water, 4.18, and gaseous water or water vapor, 2.00 joules per grams degrees Celsius. All right, we would use the appropriate specific heat based on the state of matter. All right, so let's talk about phase changes. All right, some phase changes. So solid water, the ice, it can turn into liquid water by melting, and that's a process that requires energy, right? So you add some heat to something and you can melt the ice. All right, ice typically melts at room temperature because it is warmer, the surroundings, so it melts. Remember we talked about some senators using an ice cube in the middle. A senator had a snowball in the middle of the Senate to talk about global warming, and he held it there as it melted, right? We know that ice will just melt at room temperature. All right, and freezing is when we actually absorb the energy, right? So when you put an ice cube tray into the freezer, it kind of removes the energy from the liquid water and it turns it into the solid, right? So melting and freezing. And then from liquid to gas. Now, something I want to point out, evaporation occurs, right? Water will evaporate. You ever spilled a small glass of water and then you just kind of left it and it evaporated over time? It'll go away. All right. Evaporation occurs at the surface, all right? But we really care more about boiling, All right, so boiling, you're gonna see those bubbles. This week, if you're helping your family out with any of the cooking, if you're cooking pasta or anything like that, if you're boiling water on the stove, just kind of watch it. All right, they say watch pot never boils, but actually it'll start with a gentle boil and then it'll move into a rolling boil. Right, the gentle, you'll see a little bit of bubbles, then rolling, lots of bubbles. All right, but you want to see those bubbles. What's inside those bubbles? All right, water vapor. All right, so just H2O in the gas phase. All right, so that's what we care about boiling. And then the opposite of boiling or evaporation is condensation. You see that a lot in your bathroom. If you take a shower, take a hot shower, it gets nice and steamy. All right, you're not at the boiling temperature. Taking a shower with boiling hot water would burn your skin. All right, but the water is typically warm, so you get a lot of the evaporation, not true boiling. All right, anyway, you get a lot of steam in your bathroom and then it condenses on the mirror and you can draw little funny faces and then it kind of ruins the mirror and your parents yell at you. So don't do that. But anyway, you see that condensation on a glass. If you have a beverage with lots of ice cubes in it, in a glass cup, and in the summer, you'll see a lot of condensation. That is atmospheric water outside of the glass condensing on it because that glass is so cold. All right, but condensation, all right, that's when the gas becomes a liquid. All right, now there is sublimation. That's when you go right from solid to gas. You skip the liquid phase. All right, dry ice does that. Dry ice is frozen carbon dioxide and it sublimates. It goes from its solid form to gaseous form. It's really cold, which is why you can't touch it for that long. I have ordered a shipment of steaks, Omaha steaks. They're going to come in a cooler full of dry ice, and the second I get it, I'm going to be recording some videos with it, doing some demos with dry ice, because dry ice is awesome. So I'm really looking forward to that. More so for the dry ice. The steaks, I'm sure, will be excellent, but I'm really looking forward to getting that dry ice, and we're going to look at some videos of it sublimating. Now, the opposite of sublimation is called deposition. When you go from a gas to a solid, doesn't happen very often, though. All right, so this kind of puts it all together. All right, melting, freezing, right, solid to liquid. Now here we're gonna use, this is the best word, because we get evaporation, we get boiling, we kind of use them, vaporization, all right, liquid to gas. That's our best word since we kind of see those other two words getting used a lot, vaporization, condensation, and here we have the sublimation, right, skipping solid straight into gas, and deposition, gas into solid. So these are all of our phase change words. We should be familiar with this. So I said we're going to talk about the 3 states of matter today, and this is my favorite meme. All right, teacher, there are 3 states of matter: solid, liquid, and gas. And you got the smart kid. Actually, there's also plasma. All right, yes, there's plasma, but we don't really use it all that much on Earth. So to go to the plasma state, you need to have a gas, and you either would ionize the gas to make it plasma, or you would have to recombine it. Now, something interesting, we got solid, liquid, gas, plasma, we got all of our transitions in this slide. Now, on the right side, look, enthalpy of system. An enthalpy, fancy word for saying heat. So heat of the system. So at really low heats, we're solid. As we get higher heats, liquid, higher gas, highest heats are plasma. The only time I really worked with plasma when I was at Montana State University, one of the phases in making our solar panels, we actually had to ionize aluminum metal in a chamber for it to like adhere to the surface of our solar panels, and we used this like small chamber device that like heated the aluminum so high that the aluminum turned not only into a gas but then was ionized, so super high heat. All right, that's why we don't really include plasma that much, because it's hard to use. All right, if you microwave a grape, there's something with microwaving a grape where you can get plasma for a second, but do not try that at home. All right, I am thinking of a couple of kids in particular. Please don't be sending me videos of you microwaving grapes. Don't do that. All right, so this is what we care about: solid, liquid, gas, and I do care about heat. All right, that's something we're going to talk about. So as you heat a solid, it turns to a liquid. As you heat a liquid, it turns to a gas. So what we're going to look at is this simulator I found online. All right, so it's pretty cool. Um, we can change the states of matter. So here's my liquid, right? I see a cup of liquid and I see the little water molecules. They're bouncing around. If I make it gas, they're moving way faster, right? They're not near each other. Liquid, they're near each other. Gas, they're spread out. If I go solid, right, they're like vibrating, but they're arranged well. And I can do the transitions. Now, the important thing to note is we get the temperature up here. So the solid's at -50, the liquid's at 50, the gas is at 150, all right? So those are some pretty big jumps. So let's just see what happens if we go solid to liquid, all right? So they're vibrating. I can't really notice difference, but the temperature changes. But look at this. It's melting now, but it's staying at 0 degrees Celsius. So we see it melting here, but it's staying at the same temperature, all right? Now it looks like it's fully done melting, and now what's happening to my temperature? It's increasing, and I should see the particles start moving a little faster, right? As the temperature goes up, average temperature is the kinetic energy, their speed. All right, so again, I'm just gonna redo that same, I'm gonna go solid to liquid again. So the big thing I want you to notice, when the phase change occurs, there's no temperature change. Right now the temperature is changing, it's climbing, but once it hits 0, the temperature doesn't change until all of the ice has melted and it is all entirely in the liquid phase, all right? And it looks like it's just about there. And now that we have liquid, we see the temperature, it climbs up again, right? We are adding energy to increase the heat of the solid, to cause the phase change, and then to get the liquid to change, all right? I can go liquid to gas, all right? So liquid to gas. Right now, I have my liquid. It shows a couple of the particles shoot off. That's the evaporation, but we're not at boiling, or we're not going through a phase change until we reach 100 degrees Celsius. All right, so it's heating up. Now it's at 100 degrees Celsius. We see it's rapidly shooting off. That would be like our rolling boil. All right, and we can see the water level drop, right? Because more of the liquid is going into the gas phase. All right, and you know, since it's just a cup, it'll completely boil off. And now it is completely gone. All right, if you were to boil a pot of water on the stove and if you were to leave it there indefinitely, it would eventually completely boil to the point where there was nothing left there. All right, super dangerous, so don't try that. So we can go solid to gas, and I want you to look over here on the screen. We actually have this little curve, right? So melting is flat. We were just in solid, now we're melting. All right, and melting takes a little bit of time. We're at 0 degrees Celsius, and we're just about done melting. Now we're moving upward. We're in the liquid phase, right? Temperature is increasing, but again, we are in the liquid phase, and as we add energy, we are heating up. Our particles are moving faster. That's why we have a higher temperature, and we are heading towards the boiling point of water, right? The water didn't melt until it reached 0 degrees Celsius. That's the melting point of water, and it's not going to boil until it reaches 100 degrees Celsius. All right, so we're getting there. We're at 90 degrees Celsius, so we're only 10 degrees away. All right, now we're at vaporization, boiling. So we've gone from a solid to melting to a liquid. Now we're vaporizing, and we'll stop there because it's going to take too long. And one last thing I want to show you. We could even go backwards. I have a liquid. What happens if I go liquid to solid, if I decrease the temperature, right, by putting it in the freezer? So we see those liquid molecules moving slower. And now we see the freezing. They start organizing themselves. So we're actually going down this little graph. We're going in the opposite direction, which is totally fine. All right, so we'll stop there. So let's come back to our PowerPoint. So this is the idea of a heating curve, all right? And you're gonna be like, Mr. L, there's no curvature to it. It's just straight lines. But the idea is, as we add heat, the temperature increases for a substance. But we get two sections where it plateaus. It's a flat line, horizontal, right? Slope of a horizontal line, 0. So when we go from solid to liquid, we call that melting. All right, that'll be a flat line. And for water, it's going to happen at 0 degrees. So the temperature increases, flat lines. That's when we have solid and liquid. Then the liquid temperature increases. And again, as we add heat or energy, we get the second plateau. And that's when we're boiling, right? Or vaporizing. And so we have liquid and gas. And once we're done vaporizing, then we have all gas. All right, so this is a heating curve. It always has the same shape. All right, the three slope sections are the pure states of matter, solid, liquid, and gas, and they increase in temperature when heat's added. And then the flat sections are the phase changes where you get a mixture. You get solid plus liquid down here. You get liquid plus gas, all right? So again, it's really the flat sections that you really want to look for, melting and boiling. Boiling typically takes way more energy than melting. All right, and again, the bottom of the curve is solid, then this middle section liquid, and the top section gas. And again, the flat sections, you have both solid and liquid, liquid and gas. So that's our heating curve for water. Again, the states of matter, we saw that. Now, the arrows go in both directions. When you're in these flat sections, both states are present, and it's actually an equilibrium that you're pushing. So we can go backwards, which is why this would be a cooling curve, right? Now it's still the same, gas at the top, solid at the bottom, gas, then this flat section, that's gas and liquid, all right? So this is not boiling or vaporization, instead gas to liquid, this is condensation, and then liquid to solid, so this phase, it's liquid and solid, that would be freezing, right? So not melting, freezing. Cooling curve, it is going downward. So two very important terms you need to know. Heat of fusion, all right? This is the energy required to turn a solid into a liquid, all right? The heat of fusion for water, it's 335.5 joules per gram. You will sometimes see heat of fusions in joules per mole. We are only gonna work in joules per gram. Right? Grams or moles both represent amounts. We're just sticking with grams. And we're really only going to look at the heat of fusion for water. If we were using a different substance, it would have a different value. But we're doing water, so 335.5 joules per gram. You add that many joules of energy, you convert 1 gram of water from a solid to a liquid. Right? So that is its melting. Now, heat of vaporization, the energy required to turn a liquid into a gas. The heat of vaporization for water, 2,260 joules per gram for water. And that should make sense. We saw in earlier slides that boiling or vaporization, right, same word, requires more energy, which is why it's a longer plateau, right? So it's a bigger value. So heat of vaporization, the energy required to turn a liquid into a gas, 2,260 joules per gram for water. And again, we're not going to look at other substances. We're only going to look at water this week. All right, so let's do a practice question. How much heat is required to convert a 1,500 gram sample of ice, solid water, at 0 degrees Celsius to liquid? The heat of fusion for water is 355.5 joules per gram. So the heat of fusion, 355.5 joules per gram. And we have the mass of the water, 1,500 grams. So look at those units, joules per gram, and this is how many grams we have. So for every for every 1 gram, we need 355.5 joules. We have 1,500 grams. So the formula, now it's still Q, right? Because it's still heat that we're solving for, or energy. We could use those terms interchangeably, heat and energy. It's still Q. It's going to be the heat of fusion times the mass. So it's going to be 355.5 joules per gram times 1,500 grams. And we get 533,250 joules. You did this on the calculator. This was an easy question. All right, so it's not that bad. So pretty straightforward formula, just a multiplication. So let's do a harder question. Now it's going to look similar, but we're going to break it down. How much heat is required to convert a 1,500 gram sample of ice, solid water, at negative 10 degrees Celsius to liquid at 35 degrees Celsius. The heat of fusion for water is 355.5 joules per gram. I want you to think about something. The solid water, the block of ice, it's at negative 10 degrees Celsius. If we add heat, right, if we add energy, the first thing that block of ice is going to do is it's going to increase its temperature. It cannot melt until it's at 0 degrees Celsius. So this is actually going to be a three-part question. First thing's going to happen, we need to get the solid from negative 10 degrees Celsius to 0 degrees Celsius. It will not start melting until we are at that melting temperature. Then we need to go from solid at 0 degrees Celsius to liquid at 0 degrees Celsius. This is the flat section on the heating curve, right? This is the section where you have a mixture of solid and liquid. The temperature does not change until we've converted all the solid into liquid. And then we need to take that liquid at 0 degrees Celsius and we need to heat it up to liquid at 35 degrees Celsius. So three parts to this question. Negative 10 to 0 for the solid, solid at 0 to liquid at 0, and then liquid at 0 to liquid at 35. All right, we're going to need to know the specific heat for the solid water. That's 2.11 joules per grams degrees Celsius. We're going to need to know the heat of fusion for the solid to liquid, which it's given, 355.5 joules per gram. And we need the specific heat for the liquid, which is 4.18 joules per grams degrees Celsius. All right, so part one. We're using the formula Q equals mc delta T. We reviewed it at the beginning of this video. We've seen it in the past. We are good to go here. Mass, 1,500 grams. This is the sample of ice. The specific heat for ice, for solid water, 2.11 joules per grams degrees Celsius. And the delta T, all right, well, it's T final minus T initial, all right? And the final temperature of the ice, right, not of the whole thing, but just of the ice is 0 degrees Celsius. The initial temperature of the ice was negative 10, so 0 minus negative 10, we get a double negative. All right, the change in temperature, 10 degrees Celsius. We plug it all in, mass, 1,500 grams, times 2.11 joules per grams degrees Celsius, times 10 degrees Celsius, we get 31,650 joules. That's the amount of energy to do part one. All right, that's the amount of energy just to get the solid water, the ice, to the point where it can start melting. All right, part two, this is the melting. Heat of fusion is 355.5 joules per grams. This should all look familiar. The block of ice is 1,500 grams, right? Q, because it's still heat, equals enthalpy, or equals, excuse me, the heat of fusion times M. So it's 355.5 joules per grams times 1,500 grams, 533,250 joules, all right? Just like our previous one, all right? Because our previous one had us already at 0 degrees, right? It was already ready. Part three. So now we've heated up the block of ice from negative 10 degrees to 0 degrees, and we've melted the block of ice. It is now 1,500 grams of liquid water at 0 degrees Celsius. We want to get it to 35 degrees Celsius. Q equals mc delta T, all right? Q, our energy. The mass, it's still 1,500 grams. The mass does not change in these questions, ever. The specific heat of water, right, because it's in this new form, it's 4.18 joules per grams degrees Celsius. And the delta T, T final minus T initial. What's the initial temperature of this liquid water? Well, it just finished melting. Its temperature right now is 0 degrees Celsius. That's its initial temperature. Its final temperature will be 35. So 35 minus 0, just 35 degrees Celsius. Plug it all in. 1,500 grams times 4.18 joules per grams degrees Celsius times 35 degrees Celsius. And what do we get? 219,450 joules. So just to recap, these are our answers from all three parts. Part one, 31,650 joules. Part two, 533,250 joules, and part 3, 219,450 joules, right? We have to add all the answers together. So this is how much heat's required to get from the -10-degree solid to the 35-degree liquid. It took 3 steps. We add them all up, 784,350 joules. And we'll get some pretty large numbers. So sometimes people will use kilojoules. I'm not going to worry about it, but kilojoules is just dividing all of these by 1,000. So 31.65 kilojoules, 533.25 kilojoules, 219.45 kilojoules. Answer 784.35 kilojoules. All right. So what you should be able to do. You should be able to do some of these practice questions. Your weekly assignment this week will be the 5-step from a solid all the way up to a gas. All right. But I won't give you, besides the weekly assignment, you won't have to do more than 3 steps. You might have to do a 2-step, maybe a 1-step. The other thing, I do expect you by the end of this video to have a good idea of this shape. This is the heating curve shape. This is a substance different from water. And if you look at it, you should be able to identify this is the solid, this is the liquid, this is the gas, and the 2 flat sections are the phase changes. And I would expect you, so this is going from solid to liquid. I would expect you to be able to tell me the melting or freezing point. And you would just look at the temperature, oh, it would be 120. And I would expect you to be able to tell me the vaporization or the condensation temperature. I'm looking at my second plateau. You would just read its temperature, 250, right? So you should be able to look at a heating or cooling curve and be able to answer questions like which state of matter is which section of the graph, and what is the melting point, what is the boiling point. All right, and this last graphic, this is for pure water, right? Here are all of the formulas you need. So if you're in the solid phase, MC delta T. If you're trying to go solid liquid, if you're melting, mass times heat of fusion, liquid, MC delta T, liquid and gas, boiling, M times heat of vaporization, and gas, MC delta T. And here's all the reference, right? The specific heats for solid, liquid, and gas, and the heat of fusion and heat of vaporization. All right, so you should be watching this video and then moving on to the practice to make sure that you can do these calculations and you can interpret the information on a heating or cooling curve graph. All right, so good luck with those assignments this week, class.